All right, this is going to be the final part. We're going to be graphing the Crank-Nicolson method. So first off, we're going to have to set out a few variables, like nt is equal to, let's say, 1,000. Nx is equal to 100. Delta x is going to equal, since it's a 50-meter rod, it's going to equal 0.5. And then delta t is going to equal, so we'll say 0.5 again too. So we'll have 2,000 seconds again. You have to define what R is, and for the Crank-Nicolson, since we're taking the averages of the times for the temperatures, the R is going to be alpha, so thermal diffusivity, times delta T divided by delta X squared, all divided by 2, right? Because it's the it's just divided by 2 because it's the Crank-Nicolson method. The X is going to be np dot range from nx times delta. We should set up 50 points, right? Yeah, 0 to 50 at 0.5 increments. And then T is going to equal np dot full. The shape is going to be nt no. It's going to equal nx 20. Yeah, so it should fill it all the way up to 20. Where the first increment is going to equal 0. Our first increment is 0 in the index. It's going to equal 50 degrees Celsius, and then T -1, which means the last one, is going to equal 80. Right? Yeah, I should switch it around. And then we didn't define thermal diffusivity. Alpha is going to equal 1. Okay. Now we'll make a matrix for the values with this data. So we'll do A is equal to np dot zeros. It's going to be 3 columns, to the left, to the middle, and to the right, or the lower, middle, and upper bounds. It's going to be 3 columns, and then, or 3 rows, and then the amount of columns is just the amount of nx values we have. However, we're going to subtract 2 from it because we already have the upper and the lower, which is the lower is 50 and the upper is 80 up here, right? Maybe just another. I think I ran into that before. There we go. There we go. Now we got 3 columns, 3 arrays. Okay. Now we can do our three diagonals, where A from 0, then everything before 1, or before negative, no, before 1, yeah. A 1 and on, and then a 2 and everything before negative 1. This is 1 and on. There we go. Is equal to negative r. This one is equal to 1 plus 2 times r from the Crank-Nicolson equation. Or actually, these are all from Crank-Nicolson, because when we subtract it to the other side, it's negative r, and then 1 plus 2 times r. So, negative r. There we go. For the other side of the TJNs, B is equal to NP dot zeros of NX again, minus 2, because we don't have to incorporate the first and the last one until later. The equation for B is going to be the Crank-Nicolson part to accept on the other side. So it's going to be B, 2, and on, plus 1 plus 2 times r, and then plus the middle, which is going to be 1. Right, this is the TJN regular 1 to the last one, and then plus whatever is before the last one. So B negative 2. Okay, yeah, that worked out good. So now we need, what are the first and last ones? B 0 and B negative 1, the first and last. Well, B0 is just going to be B0 plus R plus what we got up here. Like we already set T0 is equal to 50, so it's whatever times R times T0 is, which is going to be R times 50. It's the same thing there, except to be negative 1 plus R times T0, or T negative 1. Okay, and that sets up the array for the other side, and now we'll just make some plots. All right, we'll do fig 2 dot add scatter x equal to x, y is equal to t, and then name is equal to, it's going to be initial line. There we go, 50 to 80. Exit out of that. I'll do, oh shoot. This should be R times T, actually. This should be T. This should be R times t, because it's the t array, not the b array that we're adding the b array. We're adding to the b array with using the t array. So for I in range of nt plus 1, the right thing for t and nt, all that jazz. Now we're going to use the function or SciPy function called solve banded. Solve banded, which is you put in the parameters, so it's going to be 1 and 1, and then what we're drawing from A and B. Solve banded is not defined. Okay. From SciPy dot lenl g, you're going to import solve banded. Now we'll run it through again, and it's good this time. Now we'll just bring all this down. Just going to run through it all. There we go. And we can just do the same thing again for modulo if I is a multiple of 100 equals 0. I'll just bring this down, copy, paste, and instead of the name being that, it will be F for I times delta T S. All right. Now we do Fig 2. That will show the plot, but we don't have any of the lines, which is kind of a big part. So why do we not have our numbers in there? Go through solve banded. Oh, it's because it doesn't have an array to pull from. One to -1. That's not right either. No. Is it? Let's pull in this stuff again. So I'm just going to control save and then restart the whole thing. Should come out to that, yeah. And that is our more stable Crank-Nicolson method way of doing it.